Now, Heine-Borel was especially simple, closed and bounded. Is every compact set closed in general in any topological space? Do we know something about that? Did we see any examples supporting closedness of compact sets, or to the contrary, giving counterexamples to that? Now we had go back to the indiscrete topology. Cap X, the indiscrete topology, that's the open sets are just the empty set and the entire set, right? Everything intermediate, non-empty, but not equal to the entire set, is neither closed nor open. Well, for our purposes now, it's not closed. Is it compact? Yes, because there are only finite open collections, finite collections of open set, the empty set and Cap X. You have three, the empty set alone, Cap X alone, the empty set and Cap X. Well, if any one of them is an open covering for a set, well, then that's also itself a finite subcovering for the set. So compactness in general does not imply closedness. But for metric spaces, it does. Because the first part of Heine-Borel, compactness implying closed and bounded, as I said, that's true for all metric spaces, the proof there. So metrizable topological spaces, in metrizable topological spaces, compactness implies closeness. But for all topological spaces, the notion of closedness is, in a vague sense, closer to compactness than is openness, as will our next theorem show. Let X tau be a topological space K, a compact subset of X, and A, a subset of K. If A is closed, then A is compact. So closed subsets of compact sets are compact all the time, everywhere, in all topological spaces. The proof is simple. Assume that A is closed. We wish to show that it's compact, so let's take any open covering of A. Now let G be any open covering of A. If we can show that this has, but before, now let me do it now. Case 1, A is empty. Well, then A is compact. So that's the trivial case. Now assume that A is not empty. let me get rid of this trivial case at the outset. Okay. Now we wish to show that this G has a finite subcovering for cap A in order to conclude that cap A is compact. But if we can produce, using this script G, which is an open covering of cap A, an open covering of cap K, which is compact, then that will have a finite subcovering for cap K. Maybe we can actually deduce some finite subcovering of G for A. Well, here, this is the space. Say this is K, and this is A. Now, well, this is actually some open covering of A. Of course, this need not cover K. But A is a closed set, so its complement is open. If I actually adjoin that to script G, I will get an open covering of the entire space, well, thus in particular of K. Now set G prime equal to G union X minus A. Now G prime is an open covering of X, thus of K also. We'll take any point in cap X. Well, it might be outside A, then it will belong to here, but if it's in cap A, well, it will belong to some open set in here, okay? But since K is compact, G prime has a finite subcovering say G1 up to GL for K. But of course, this collection may contain X minus cap A. One of the G sub i's for I from 1 to L might be X minus A. But then I will delete that. But is it possible that this just consists of X minus A? Well, that's not possible. If that consisted of just X minus A, since A is non-empty and contained in K, it would not cover K. Now, if I take this finite subcollection, delete from that X minus A, this will be non-empty and a finite subcovering of G, of this original open covering, for A. Thus, A is compact. So this much for closedness in Heine-Borel, closed and bounded. For boundedness, we had noted, we had recorded a problem that actually was associated with boundedness. And the example was this. Take N, take D, this is the usual distance. So So for any xy in N, the metric dxy is the absolute value of x minus y. But we also had an M where this was the discrete metric. Now, we noted that the two topologies, the collections of open sets induced by this metric and this metric, were the same. So they're topologically the same. But N was not bounded with respect to D, while N was bounded with respect to M, because this only takes on two values, 0 and 1. Just take 1 for any xy, mxy is less than or equal to 1. So boundedness is not a topological notion. It does not stay invariant under equivalence of metrics. It depends upon the particular form of the metric we use, although they might induce exactly the same collections of open sets, is not a topological notion. Now the question then is, the simplicity of Heine-Borel is so tempting, whether we can modify the notion of boundedness, say bounded prime, such that bounded prime and bounded coincide in Euclidean spaces, because we wish make no harm to the function of boundedness as in Euclidean spaces. They might coincide there, but they might differ in general metric spaces. Possibly, bounded prime might be a topological concept, may stay invariant under equivalence of metrics, but more important than that, maybe we can get Heine-Borel prime theorem, which would say, well, a set in a metric space is compact if and only if that set is closed and bounded prime. Okay? Now we'll make such an attempt. Well, it will take us to somewhere, but not solve the entire problem. So that takes us to a new section. 1 point something, 11 or 12, I don't remember. The title is Total Boundedness. Now let us start right away with the definition. So we need the metric space. And we need some subset A of cap X. Now we say that A is totally bounded with respect to M if A is either empty or there is a finite non-empty First I need some quantifier. Let me write that at the beginning. Or for every epsilon positive, there is some non-empty finite subset E of A such that if I take the union of the epsilon balls about X, when X is in that finite subset cap E of cap A, this contains A. Now, if we define union of sets over the empty collection as the empty set, we do not need to make this distinction. But let's make it, because here in this case, we require the existence of some non-empty finite subset E, okay? Because if A is the empty set, there will be no finite non-empty subset of the empty set, but the empty set should be regarded as being bounded. So that means, given any epsilon, we find finitely many points in the set, then we take the epsilon balls about them, and if I take the union of these epsilon balls, it will cover the entire cap A. Now let's just get back to here and let's ask the following. Is N totally bounded with respect to the discrete metric? Is it? No. Because if I take epsilon less than 1, and if I take any finite subset of N, then each epsilon ball about any point in that finite subset, that will just contain from the set of naturals the center X itself. Just it will be 1 point. So, the union of one element sets, that will be finitely many. That will be a finite set. That cannot contain N. So, the first remark is, check that N is not totally bounded with respect to the discrete metric. We do not know whether this total boundedness will do the job we expect from it, but at least this discrepancy, that disappeared. Now, first, a simple proposition. At 2 levels, statement 1, let A be a subset of some Euclidean space. It is easy to show that A is bounded in the previous sense, in the former sense, if and only if it is totally bounded with respect to D. So boundedness and total boundedness, they will coincide in Euclidean spaces. Now, A is bounded with respect to D, the usual metric, if and only if A is totally bounded. With respect to D. The second statement, well, total boundedness is stronger than boundedness. That is, total boundedness implies boundedness. Do we know that? Now, we had a lemma saying that if you have finitely many points, and if you take m balls about each of them, if you take the union, it will be some such set that will be bounded. Well, but if A is a subset of a bounded set, A will be bounded as well. So that's our second statement. Let Xm be a metric space, a subset of X, if A is totally bounded with respect to M, then A is bounded with respect to M. The proof of both, well, we have actually gone through the proof of the second statement in words, but formally I leave that as an exercise to you. The next natural question to check is whether the total bounded version of Heine-Borel theorem will be valid in general in metric spaces. That is it true in a metric space that a set is compact if and only if it's closed and totally bounded? That in general, unfortunately, will not be the case, but one direction that will hold. Let Xm be a metric space and a subset of X. If A is compact, then A will be closed and totally bounded. Proof. Assume that A is compact. Now, for closedness, just see the proof of Heine-Borel theorem, because compactness implying closeness, we just use the metric properties of D. To show that A is closed, replicate the proof in Heine-Borel theorem by replacing D by M. Well, we showed that a compact set was bounded, again, just using the metric properties of the usual distance, but now this is more demanding, this is stronger. This says it's not only bounded, more than that, it's totally bounded. But the proof of that is immediate. Take any positive real number epsilon. Now, G the collection of all epsilon balls when X is in the set A. This is a non-empty collection of open sets. If A is non-empty, well, again here let me, when A is empty, A is totally bounded. Otherwise, take any epsilon positive. Now this is an open covering of cap A. This is a non-empty collection of open sets. Moreover, for each X in A, there's an epsilon ball here which owns X as its center. Is an open covering of A. So there is some finite subcovering, there is some non-empty finite subset E of A with union of the epsilon balls about X with respect to M. When X is in E, this contains A. But that's nothing but the definition of total boundedness. So A is totally bounded. Completing the proof. But the converse, that will not hold. In general, in a metric space, we can have a closed and bounded set which is not compact. So we'll continue by giving an example of that phenomenon. Well, following that, we will actually single out a class of metric spaces where compactness will turn out to be equivalent to the conjunction of closedness and total boundedness. They will be the so-called complete spaces. But here, whatever complete means, the example of a metric space where the converse of this will not hold, that must be an incomplete space. Well, if you use everyday words and forget about formal definitions, do we know examples of incomplete spaces which have gaps everywhere? Well, if you take R, if you take the set of rationals, they have lots of gaps. If you take any two rationals, there are irrationals between them. Well, or if you take irrationals as well, if you take any two irrational numbers, there are rationals between them. So we'll take our example from the metric space where the space itself is the set of rationals and the metric is the usual distance. Now consider Q. QD. Well, then we need an example of a set which is both closed and bounded, totally bounded, in fact, but not compact. Now, that set we can take as the intersection of the interval from square root of 2 to square root of 2 plus 1, intersection Q. We know square root of 2 and square root of 2 plus 1 are irrational numbers, so it makes no difference in defining this set whether I include them or exclude them, because they are excluded in any case since they are not in Q. Is this closed? Let's be careful and let's check. Let's use the sequence yardstick. Assume that Xn is a sequence in A. So each Xn belongs to this set such that Xn converges to A for some A where in this space. Okay? Well, then, since the sequence is convergent in this space, the limit belongs to Q. It's rational. So to conclude that A is in cap A, what remains to be shown is that it's in this interval as well. By construction, for all n in n, square root of 2 is less than or equal to xn, less than or equal to square root of 2 plus 1, because xn is in this set. So every point, every xn satisfies, is in here, satisfies this. But by one of our propositions in the section on sequences, well, if this holds, then the limit also obeys this inequality. By a previous proposition, we have that square root of 2 is less than or equal to A, less than or equal to square root of 2 plus 1. So, A is in cap A. It's in Q and in this interval as well. Thus, A is closed. Is it open? Yes. How can we show that? Pick any x in A. Can we find an epsilon ball about x which entirely stays in here? Well, x is neither square root of 2 nor square root of 2 plus 1 because x is in Q. Now, square root of 2 is less than x and that's less than square root of 2 plus 1. So there is, I can take just this minus this minus this, the smaller one of those, but there is clearly, there is some epsilon positive such that b d epsilon of x will stay in square root of 2, square root of 2 plus 1, intersection Q. Because here BD x epsilon, we are in here, by definition this is the set of all x in Q such that the, well, let me write y here, I use y in Q such that dyx is less than epsilon. If we define an epsilon ball in a metric space, that epsilon ball consists of points belonging to the metric space, which in addition satisfies some closeness condition. But here, the space is this. So, I want to show A is closed. I'm sorry. Well, A is open, but that was, A is both open and closed. But we need, what we need is that this is closed and bounded, but not compact. Well, so let me do it like this. Pick any x in Q minus A and show that Q minus A is open. We showed that it's closed. We need to show that it's bounded, totally bounded. I'm sorry. Well, it's open, but that's irrelevant. We need to show that it's totally bounded, but let's do it. This is square root of 2. This is square. That was just restation for the exam, what we did. Square root of 2 plus 1. Now, I will not write the whole thing in full, but I will show you how to write it. Well, let epsilon greater than 0 be given. We need to find a finite number of points in the set cap A, such that the union of the epsilon balls about those points will contain A. Now, there is some n. Well, let me write cap n in n, such that 1 over n, that's less than epsilon. Well, then, let me partition this into subintervals of equal length, each of them of length 1 over n. That is, let's partition this into cap n subintervals. Will each subinterval contain a rational number? Yes, because this is less than this. There is, well, could be the partitioning points as well, but each of them contains something in Q. If I take epsilon balls about those points in this space, well, the epsilon ball about this, well, the whole thing is, it will contain this interval entirely. Because 1 over n, the length of the interval is 1 over n, that's less than epsilon. If I take epsilon as the radius, it will contain the entire subinterval, but that will be the case for each, so it will contain this intersection. So check that. is also totally bounded. Well, for this to do the job, this example, it should not be compact. Can we easily show that? Now, for each n, let me do this. This is square root of 2. This is square root of 2 plus n at plus 1. Now let me, for each n, let me consider square root of 2 plus 1 over n. If n is 1, you're here. If n is 1/2, you're here. If this plus 1/3, and so on. And let me take this portion. Set Gn equal to the interval from square root of 2 plus 1 over n and up to square root of 2 plus 1 intersected with q. Well, again, I may or may not include this, but they will be excluded since that will be the same set since these two numbers are not rational. Well, you can easily check as, now we can use what we did in here. Well, these will just be open. Okay, now check that. Gn is open for any n in n. Will they cover the set? Well, take any rational number in this interval. Well, then take just n large enough such that square root of 2 plus 1 over n falls to the left of this. Then it will be in Gn for such n. So clearly, Gn n in n is an open covering of A. Does it have a finite subcovering? Well, let's write that part in full. Suppose there is a finite, non-empty subset E of n such that if I take Gn n in E, that covers A. But by construction of this, set, well, cap L equal to the maximum of E. So this is a finite non-empty subset of natural numbers. There's the largest one, set L to that. But here, this is this union, n is in E, that will be equal to, according to that, square root of 2 plus 1 over cap L, because as n gets larger, incidents get larger. So it will be this square root of 2 plus 1 intersection Q. But now, this is square root of 2 plus square root of 2. This is square root of 2 plus 1 over L. This is positive. What do we know about this interval? It contains rationals. However, A intersection square root of 2 square root of 2 plus 1 over L. This is not empty, so it contains points of A, so this cannot be the case. This has points which are not in this set, as that set is equal to this. A contradiction. So we have exhibited one particular example of an open covering which has no finite subcovering for the set in question. Thus, we conclude that the set in question is not compact. So G has no finite subcovering. For A, thus A is not finite. That concludes this example. But here we'll see that this behavior actually stems since rationals are not complete, in the sense that no matter how close two rationals I take, there will be between those points which are not rational. There will be points missing. There will be gaps. In that sense, the set will not be complete. But I guess we can stop at this point. So I wish you success and luck in all the exams next week.